Thank you, Sang-il, to invite me to give a talk. I would like to talk about the directed tangles and applications, which I worked a lot in the last year. So it's a joint work with Arcontia Gianopolo, Kenichi Karabashi, Stefan Kreutzer, and Kukinji. Yeah. So I remember that exactly 10 years ago, I started the master program, and Sang-il gave me this graph minor 10 paper, and we tried to read the paper, and it was about the tangles for undirected graphs. And well, yeah, I was quite interested in the trees and rank width or the width parameters, and so it was quite interesting, but on one hand, it's quite abstract, so at that time I was quite hard to understand. But later on, I was interested in the packing and covering problems, and then tangles are the fundamental tool in the problems. And so I become too interesting more than before. And so when I started a postdoc with Stefan Kreutzer, he is quite interested in the generalizing all these things to the directed graphs, and we worked a lot on the directed graphs. This is the main topic on the talk. So I think most of the students don't know about the tangles. Yes, so I just take some time to explain the undirected tangles and then switch it to the directed graphs. So we start with the definition of separations, which is easy. So separation is an ordered pair of vertices, A and B, such that the A union B covers all the vertices, and there are no edges between A delete B and B delete A. So, like the picture. And so using the separation, the order is defined as the size of the intersection. So using the separation, what we want to do is that we want to indicate some area containing some high connective structure. So we will see what are the high connective structure later on. So here, just let's imagine that the clique of size, huge size, like clique of size. One of the clique is a set of pairwise adjacent vertices. And you can easily observe that this clique should be fully contained in one of A or B, right? So because separation is a small order, so actually it doesn't matter for the order for the cliques, but what we want to say is that the high connective structure actually essentially lie in one of AB whenever AB is a separation of small order. So does it make sense? Yeah. So if you look at the global picture, then so this is the simplest case where the graphs are decomposed by cup vertices, and then the clique is contained in some block, right? So how to indicate this block, right? So the way is that you can consider for every cup vertex, you naturally make a separation with the intersection is the cup vertex, right? Like in the left-hand picture, you can think about the separation A and B, and you can say that B contains a clique. And for the right-hand side, you can consider C and D, then D part contains a clique. So considering all such separations, you can indeed indicate the area containing this clique, right? But this separation of order 1 is a quite extreme case. We are thinking about separation of order and most T for some T. So you might have some intuition of the definition for tangles. So here is the definition for tangle. So tangle of order T is a set of separations of order less than T. So less than T means that some small separations, where the first condition is that if AB is a separation of order less than T, then the tangle contains exactly one of AB and BA. Right. So the meaning of T contains some separation AB is that the B part contains the high connective structure where we want to indicate. So we say that whenever you have a separation, exactly one of the part contains a high connective structure. So it fits to the definition, the condition 1, right? So we do not contain both AB and B. So whenever you have AB is in D, the tangle, so we usually, for this reason, we usually call that the A the small part and B the big part. Yeah. And then the second condition is also necessary that if you have three separations in the tangle, then the union of three subgraphs induced by the small size do not cover the whole graph. So this is some necessary condition. So there is some reason why we needed this, but maybe just skip for this. So I want to give some example. With a simple example, if you think about the cycle, then you can easily define a tangle of order 2 for the cycle. So for tangle of order 2, you have to consider all separation of order less than 2, right? So the separations should have order 1. So because it's 2 connected, all possible such thing is that the one vertex and whole vertex. But then you just collect all possible one vertex, comma, whole vertex, will give a tangle, right? Any of three separations do not form the whole graph, right? But you can argue that it does not give a tangle of order 3. So why? Suppose some tangle of order 3 exists, then so you have to consider for every separation of order 2, one of the AB or BA should be in the tangle, right? So you can think about, to obtain a contradiction for the second condition, you partition the cycle into the 3 passes, and then put on the small part. So let's say A, B, C, D, and D, E, F, G, and G, H, A. Then because the second condition does not hold, one of the 3 parts does not in the tangle. So let's assume that the first blue separation does not in the tangle. Then by the first condition, the opposite of this separation should be in the tangle, right? Because for every separation of order less than t, one of them should be in the tangle, right? So it's in the picture. So D, F, G, H, A is in the small part, and then other part is the big part. And then we just remain the big part into a 2 part, like AB and BCD. Then again by second condition, one of them should not be in the tangle, and then we obtain a contradiction because if the opposite of this blue guy is in the tangle, then this is a whole set which already contradict to the second condition, inducing the whole graph. Yes, so the maximal tangle that I have for this cycle is the tangle of order 2. So what about the complete graph? The complete graph, so you can check that it gives a tangle of order 4, but does not give a tangle of order 5. Because you cannot cover the whole complete graph of size 6 by triangles. So if you have a separation of order 3, then that will be three vertices and whole vertices because of the clique. But then you cannot cover the whole complete graph by 3 triangles, but can cover by 3 K4s. So, and then in general, if KT give a tangle of order K, whenever K is less than 2T over 3 plus 1, but does not give a tangle of order exactly 2T over 3 plus 1. So actually the tangle the maximum size of a tangle is equivalent to notion of tree width, because if the size of the order of tangle is large, it means that you cannot easily decompose into the tree-like way, so it naturally corresponds to a tangle, tree width. So I denote by T and G as the maximum order of a tangle in the whole graph, and tree width is the TW. Yeah, I don't want to define a tree width. And so Robertson and Seymour at the beginning of the paper, they proved that the tree width plus 1 is at least the tangle number, and at most 3 tangle number over 2. And then the right hand side is tight because of complete graphs that I explained. Yeah, also left hand side is also tight. But this is not the end of the story. So what they want to do with the tangle is the more global picture, where we see that the one tangle corresponds to one area of high connective structure, but in the whole graph, it might have many high connective structure. they can be separated by a small separation. So we say that they are different high connected areas. So the question is that could we present all tangles together in a one picture, right? That might be some interesting thing, because one tangle just give the one area. So to do this, we have to compare with the tangles, because we have two high connected areas, and then we want to say they are different areas. And so using the separations. So we say that two tangles, T1 and T2, are distinguishable if there is some separation AB, where AB is in the T1, but the BA is in the T2. But this looks like this picture, where because AB is contained in T1 means that the area with respect to T1 is on the B side, right? While the T2 is on the A side. So in the picture, it looks like this separation separates these two areas, right? So in this situation, we say that the separation is a T1, T2 distinguisher, and otherwise we say that indistinguishable. And if indistinguishable case, one is contained in the other. And we are interested in the distinguishable minimum order among all distinguishers. So what Robertson and Seymour proved in the last step in the paper is to obtain a tangle tree decomposition. So every graph admits a tree decomposition L, BT, where BT denotes the backs of the tree decomposition, such that there is a bijection from the set of maximal tangles to the nodes of the tree. And so if two tangles, T1 and T2, are distinguishable, then so they are corresponding to distinct nodes, right? And then there is an edge on the path in the tree decomposition where this edge corresponds to the minimum or the distinguisher between the tangles. So yeah, basically they explain this with some more condition, but just in one slide I just write some essential things. And then also for every edge in the 3D, sorry, this should be L. For every edge in the tree decomposition, there are two maximal tangles that are separated by the separation corresponding to this edge. Yeah. So they use the tangle tree decomposition to obtain a graph structure, famous graph structure theorem. So along the all graph minor papers, they prove that so they want to prove the Bargan's conjecture, and to do that, they obtain a structure for the H minor free graphs for fixed graph H. So very briefly, what they do is that they first apply the tangle tree decomposition, and then for each bag, so because of the property that it corresponds to the maximal tangle, so they argue that if you forbid some minor, then the bag should be almost embeddable on some surface. Yeah. So I just want to mention that the tangle tree decomposition is used in the graph structure theorem. So our question is that what about directed graphs? Can we define a tangles for directed graphs, or tangle tree decomposition, or some structure theorem for digraphs? So this is quite possible questions, right? Do you have any questions so far before going to the directed graphs?
One question about this.
Yep.
So the tangle is a set of these separations.
Yes.
In the pictures before, it kind of looked like the tangle was a subset of vertices. Here, why does it look like? So
yes. So that's a good question. Maybe go back to the this lower picture, right? So using all these separations. So separation, like I want to include the tangles C, D, not the D, C, because the D part contains this clique, right? So by all the separations to indicate this side, so we can actually point towards to this block. So you can indicate really this vertex set. So yeah, that was also difficult for me at the beginning. So tangle corresponding to some real part in the whole graph. Yeah.
Tangles are much more fuzzy than vertex. So for example, there's still a famous, very simply stated open question whether for every tangle you can find a vertex sets which decides the tangle, in the sense that whenever you look at a separation, more than half of the vertices from your decider set are on the side where the tangle points to. And that's still open. So
yeah. Thank you for questions. Yeah. So we start with the directed separation. So for digraph, we also think about the pairs of vertices A and B. But first, we define that some edge crosses from the A to B, where its tail is in the A delete B, and its head in the B delete A. So the black edge on the picture. So the tail is in the A delete B, and the head is in the B delete A. So whenever you have such an edge, we say that this edge crosses from A to B. And directed separation is a pair of vertices, ordered pair of vertices, such that it covers the whole set. And there are no crossing edges from A to B, or there are no crossing edges from B to A. So basically, the intersection blocks one direction of the edges. So this definition is, you didn't define this, so you can think about the Mengel theorem. So this about the directed separation, right? So you have two sets A and B, then either there are many vertex difference passes from A to B, or otherwise you have a directed separation of small order, which blocks edges from the side for A to the side for B, right? So in some sense, directed separation is quite natural to work on the directed graph. Yeah, and we need a few more notation where that we want to describe the part allowed edges from somewhere to somewhere, because we block the only one direction of edges, so the other direction, so you might have arbitrary edges, right? So when there are no crossing edges from B to A, like the figure, we write A part is X plus. So X is the separation in the one word. So we write the A part is X plus and B part is X minus, meaning that we allow edges from X plus to X minus. It made it confused. We had the time to decide this plus, which part is plus or minus, but just we decided like this.
yeah, well, both sides.
Side we just choose arbitrarily for the one side to be plus and to other part minus, and order is the size of the intersection. And for separation AB, X is AB, we denote by X star is the opposite BA. And then we define a tangle quite similar to the undirected tangle, where tangle of order K is or the separation, directed separation, set of directed separations of order less than K, where that for every directed separation, one of them, T contains exactly one of them. Sorry, actually it implies by two. So I want to change, but I didn't. Yeah, T contains exactly one of AB and BA. And also the second condition is slightly different. So whenever you have three separations, the union of A1, A2, A3 is not equal to bridging. So we don't care about the induced subgraph for each small part, but just to say that the union of three parts is not equal to bridging.
So there is possibly edge from the small part to the big part, or big part to small part. Both are allowed. Both are allowed.
Yeah, both
possible. Yes. So for every separation, only one direction is blocked, and then I don't know which. Maybe small part to big part there might be edges, or the big part to small part there might be edges. So that's why it's a very complicated undirected graphs. Yeah. So I want to remark that actually for undirected graphs you can define also with this condition, but the size of a maximum tangle will be the constant So it's equivalent to the original definition of the constant vector. But the original definition defining by the induced graph for the small part, so the maximum size of a maximal tangle is the same as the branch width of the graph. So that's why the way of defining the induced graph is useful. But for here, we cannot define, so it's quite complicated to define with the induced graph here because we mostly didn't cover whole the graph because for any separation, we have arbitrary edges from the one side, right? So how to describe these edges, right? So to avoid that, so we just say about the union of three vertices, small part will not be the whole vertex. And yeah, two tangles are distinguishable if there is a distinguisher. It's the same. So at this point, I want to remark that there are two big differences between the undirected part and then directed part whenever you have two separations. So the left-hand side is the for the undirected graphs. Imagine that you have one separation AB and the other separation is CD, and then they are crossing and then making four different parts. But in this case, what you can do is that whenever you choose one of the four corners, like A intersection C, left apart, right? So we can take A intersection C and then taking a rest on the other part, you can make a separation. This will be a separation because all the vertices on the boundary will block the all edges anyway, right? But for the directed graphs, it's not true because it depends on which edge is blocked, right? So we have a separation x plus x minus and y plus y minus. Then the intersection of x plus and y plus and the rest give one separation. And then also this gives a separation. But this intersection of x minus and y plus does not give a separation because so you can come back to here and then go out like the other part, right? So this makes a big difference between the undirected graphs and directed graphs. Yeah. So before going to state our main result, I would like to explain the directed tree decomposition. Maybe too specific, but just I give you briefly. So directed tree decomposition is so this is an example where you have digraphs, and this is a directed tree decomposition where you have a rooted tree L, and then two functions beta and gamma, where beta is you assign the vertexes of the graph into a nodes, like a undirected tree decomposition. And gamma is the assignment of vertexes to the edges of the tree. And then the first condition is that the nodes for vertexes on the nodes form a partition of the graph. And then for every edge in the tree, so if you take all union of the backs below this edge, so say B, then there is no closed directed walk containing both B and the rest. All such closed walk is blocked by a gamma E. So gamma E is sometimes called guard because it guards a possible walk from the below and then above. Yeah, I want to pure remark here. So the original definition does not allow the empty set, but it will be equivalent of some constant with this definition, this relaxation. And also you can remove the closed property in the walk, but it's also equivalent. So because of some convenient property, we just push it to have a closed directed walk here. And to define a directed tree width, we usually consider that for every node, you take a union of this back and then all the guards in the incident edges. And then the maximum among all of them will be the width of the decomposition, and then directed width is the minimum width among all decomposition. But in this work, we don't need directed tree width, but only need the size of the cards, because each bag will correspond to some tangle which is large, so we don't care. But we really care about the size of the card. So we say that the edge width is the maximum size of the card among all edges in the decomposition.
So is this definition of
The same as the definition by Robertson, Seymour, Johnson, Thomas.
It's different. So they define actually they didn't allow the empty sets, and then here is just a directed work whose endpoints are B but containing the rest. But there is later on there is some addendum for the paper that they fix some argument there by allowing empty sets, and then there is some more argument about that.
The edge. Oh, I see. The edge, which is just the size of this.
Yeah, we just consider the size of the vertexes. Yeah, on the card. I think there is experiment, but I have to check. Yeah, I didn't quite remember. Yeah.
What's then the directed tree width, or is that?
So usually the directed tree width for directed tree width, so we define the width of decomposition as a maximum among all nodes, where that you take a union of this guy and then incident cards. So like for this node 6 and 12, and then size 2 is for this node, and then you take a maximum among all nodes. That will be the width of the decomposition, and directed tree width is the minimum width of all decompositions. Yeah, and we want to distinguish tangles by directed tree decomposition in the similar manner, but actually it's more complicated than this statement, but just I write some essential things. So directed tree decomposition say that distinguish the tangles in some set of pairwise distinguishable tangles, where there is some injection, not the bijection, but there is some injection from the tangles to the node. So you assign the tangles in the different nodes in some way, and for the different tangles, there is an edge on the path on the tree decomposition, where the edge corresponds. So there is just a minimum distinguisher whose intersection is contained in the guard. Yeah, so you can say that if a guard, you can take a whole vertex set on the guard, so we can distinguish all the tangles, right? But we want to restrict the size of the guard in terms of the maximum order of the tangles. Yeah, so this is now the statement is that the tree is the digraph, and for any set of pairwise distinguishable tangles, you can give a directed tree decomposition distinguishing all tangles in T, so which has edge width at most m squared plus 2n, where m is the maximum order among all order of minimum order distinguisher between the tangles in T. So you consider all pairs of tangles, and there is a minimum order distinguisher, right? So among them, you need the largest size, which is m, and then we can give a directed tree decomposition where the edge width is bounded by m squared plus 2n.
is the width of this decomposition bounded?
Directed width? Yeah. So directed tree width can be large, because, so I mean, we just care about the edge width because some part has like a huge bidirectic, huge click, then one bag should be huge directed tree width.
What is
One bag contained all the vertices.
Then you don't distinguish it all the tangles.
The edges could still distinguish all the things.
No. So if you have two maximal tangles, you have to assign these two tangles in the different node. So it's a
The nodes, the tangles get to assign nodes. Okay.
Yeah, we have
right.
injection from the
Right,
tangles.
okay.
two. Yeah. Right. Yeah. Maybe this picture maybe help to somehow understand. So in the undirected case, what you can do is that you have a tree-decomposition distinguishing T1 and two tangles T23. And then you know that there is some separation distinguishing T23. Then so this separation is AB, and the separation separating T23 are this. So you want to further decompose this to the ABC at T1 to 3. Then because any four corners give a separation, so T1 lie on either C or D. So we can assume that so T1 is in D. Then we look at these two corner separations. Then by the submodular inequality, either one of them has a small width somehow. And then if the bottom width is small, then we just decompose T1, T3, T2 in this way. So you give us three bags in the linear array and then put the vertex corresponding there. But otherwise, if this is big, then you just assign the T2, T3, T1 in this way. So this is separating the all pairs of tangles, right? But for directed graphs, this kind of thing is quite annoying because, for instance, you have something like this, and then the separation corresponding to this is x minus and x plus, and separation for this is y plus and y minus, like this. And then assume that the T1 is on this part. But because of this plus minus things, so only this part is a possible separation, right? So then maybe this part is small and this part is large, right? So this is an annoying case. And then we actually need to extract this into some other bags. So this is basically why we need the injection for the tree decomposition, because if we put the M into the a T1 bag or T3 bag, then it will not be an exact separation. Yeah. So I want to give us some proof idea. So let's assume that the capital T is a set of pairwise distinguishable tangles. So what we first obtain is the what we call the DAG-labelling. So DAG is a directed or cyclic graph, which you can give a linear ordering of the vertices where the order is from left to right. And so DAG-labelling means that you assign all the tangles into the vertices such that for every edge we assign some gamma for the separation. And then the separation has a nice property that all the guys, whichever from the B, this head, contains the separation AB, while the other guys separate the opposite of this guy. So this is written there. So the separations gamma AB have order L. Our assign is the all the tangles whichever from B contains this tangle, this separation, while other tangles contain the opposite of this separation. I have to mention that we first think about the special case where all tangles are distinguishable by separation of order L, but not distinguishable by the less than L. So we first think about that special case and then generalize to any pairwise distinguishable tangles. And then we modify this DAG-labelling to the undirected tangle tree labeling with actually almost the same property. like undirected graphs, where that the tangles are assigned to here, and then for any pair of tangles, you can find the minimum order distinguisher on the path. So actually, so this is quite a tight result, but to modify this to the direct tree decomposition is quite complicated because the separations, we cannot always uncross the separation. So we need to extract some empty packs somewhere to make the real directed tree decomposition. So this is a whole picture. Maybe I really focus on to obtain a DAG-labelling. That might be quite understandable. And then I explain the brief picture for the later part. So let's assume that you have a set of tangles and two tangles are, we say that two tangles are L distinguishable. If there is a separate distinguisher of order exactly, and we say that L indistinguishable if there is no distinguisher of order and most L. And then we assume that the given set T is a set of tangles of order more than L that are pairwise L distinguishable but L minus 1 indistinguishable. So the separations of L are very important here. And assume that the AD is a separation distinguishing at least two tangles. And then if there are at least two tangles in the A part where then there is some separation CD such that the tangles containing CD is a strict subset of containing BA. So which means that you can exclude more than the BA separation. Yeah, I'm sure I think I can explain this lemma quite in detail. So let's assume that the separation X is AB and assume A is X minus and A is X minus as in the picture. And the case where A is X plus is symmetric, so I just do not assume. And we know that A part contains at least two tangles. And because of the assumption that any two tangles in the capital T is distinguishable, so there is some separation Y distinguishing these two tangles T and T prime. So just assign T is here and T prime there. Yeah. So we can, again, I just remind you that only these two separations can be a separation, right? So we have to use these two separations. So there are two cases where there is some tangle corresponding to this part. So in this case, what we know is that by the some modular property that, so these two order is exactly L and L, right? And then by some modular property, the sum of these two values are the 2L, right? Bounded by 2L. But it cannot be the less than L, because if the less than L, then this separation separating T and T star. But we say that any two tangles are not separated by a less than L separations. So which means that both separations should have order exactly L. And this means that if you take this separation, so this separation have tangles less than the BA thing, because we exclude this T prime, right? Does it make sense? Yes. And otherwise, all the tangles lie on the bottom part. So all containing the on this part, then we just simply take a y minus comma y plus, so that so you exclude this T from the A part. Yeah. So this is the proof of the lemma, and so the above is just the statement, and it implies that there should be some tangle T which is only separated by some separation, Because if you have a separation separating two tangles, then we can find another separation separating more and more. And then at the end, you can find some separation separating exactly one tangle from the others. Yeah. So then we iteratively apply this corollary. So we say that when you apply this corollary, so we say that T is solely separated by sigma T. So sigma T is the separation obtained by this corollary, and this excludes T from all the rest. And we say that, so we just iteratively apply the corollary that we find all the tangles solely separated by a separation from the beginning, and then say C1, and then you just forget about all the tangles in C1, and then again find the tangles solely separated by a separation. And then you just do this until there is no rank, no separation. And then the separation appeared in the case step will be called the separation of rank K. So here is an example. So you have a digraph with some 5 tangles corresponding to A, B, C, D, E. And then you have to carefully check, but I just mentioned that this A and D and E can be separated by solely separated by some separation with order 2. And then we just forget about the A, D, E, and then the remaining guys are B and C, right? And then B and C can be separated by some separation, solely separated by some separation. So they will have a rank 2. And then I will give us some hierarchy between the tangles. But then there are some tangles where that even though the B is on this part and then E was separated in the first step, right? Those separations separating somehow independent way, right? So in that sense, we say that B and E are independent. But the separation for C include a part for E, right? In this sense, we say that they are dependent. So what we actually define a descendant where that if T prime is a descendant of T, so let me say that sigma T is AB and sigma T prime is A prime comma B prime, and we say that T prime is a descendant of T if AB is in T prime but B prime A prime is in T, which means that it looks like this picture. So T prime was first excluded, and then later on T was excluded, that the area containing T contains the T prime. So T prime was first excluded. So T prime should have a smaller rank, and then later on T was excluded, but the part containing T contains a T prime. So there are some relation between them. So if one is a descendant of the other, then we say that they are dependent, and otherwise independent. In the case of independent, the always picture looks like this. So the separation for T does not contain the T prime, and then separation for T prime does not contain the T. So they should lie like this. So now we prepare to define a DAG-labelling. So we just yes, you can just see this picture where that you have these 2 steps, right? To have a rank 1 separations and rank 2 separation. I just pick all. You just put the vertices for every tangle, and then we add an edge from the C to D if D is a descendant of C. But before doing that, we just pick one of the nodes, especially on the highest rank, and then pick on the top, and then assign the sigma, change the sigma to be the empty comma whole set, so that it adjacent to all the vertices. So this is just for some reason, and so it's defined like this. So this has a natural property that, for instance, if you look at the C, then So if you look at the this edge, so B and C, we assign for every edge, we assign that gamma of this edge is a sigma of this separation. Yeah. So which means that all the guys below contains in the separation for this because of the dependency, but the other guys do not contain the separation for C. So it naturally have the desired property. And so we have to turn to undirected tree. Yeah. But it's more or less a rooted tree. But at the end, we change it to the undirected tree. So assume that you now have a DAG-labelling as before. And then we first remove all transitive edges because for the property that we have for the DAG-labelling is preserved by removing some transitive edges. So we can simply start with removing that. And at the end, if the resulting digraph do not have a node of in degree more than 1, then it will become a tree, really tree, undirected tree. So we are done. So So what we do is that we have to deal with the case where some node is in degree more than 1. So in this case, we take a topological ordering of the D prime, and then where that U is less than V means that there is no path from U to V. So you give us some ordering like this, and then this direction is a smaller part. And then you choose a minimal node which is in degree more than 1, and then choose 2 nodes which among in neighbors you choose 2 minimal in neighbors. Yeah, so briefly the real picture looks like this. So this tangle T has 2 in neighbors tangles, and then what you want is that you remove this arc and then just change it to T2 to T1. Yeah, but then you have to care about the previous edge, because the previous edge do not have to care about the T1, right? Because the T2, originally T2, there is no path from T2 to T1. But now by linking from the T2 to T1, so you have to care about this edge more carefully, because it has to contain the T1. So we prove some lemma that there is some separation separating all the things, the T1 and T2 together. So I didn't write that, but we can prove something like this. Yeah. Okay, so maybe I have to skip this. Yeah. So and then I want to explain how to generalize to any pair of distinguished tangles. So until now, I just say that T was any pair of tangles separated by order L, but not separated by a separation of order less than T. And then I want to generalize to any pairwise distinguished tangles. And I need 2 more notation that this T restriction L is that you just take all separation of order almost L. And then con T is that all the tangles containing this T. So among the tangles in the capital T. So we need these 2 notions. So let's assume that M is a maximum order of tangle in T. And you can easily see that the T restriction to M, and then you take a con, it only contains a T, because any pair of T is distinguishable. So what you do is that so you inductively from M to 0, you construct the tree labeling for tangles in the con T restrict to L. Yeah. So this is a picture. So these are the real tangles in the capital T, and then you restrict to L. Then this gives us some tangle, right? So if you take maybe these 2 tangles have the same restriction or L, right? So this cone contains some tangles in the original set. I want to have a tree labeling for this guy. But now, so you go back to the L plus 1. And then, so they partition the previous tangle into subsets, right? And then by induction, you can have a tree labeling for each of these sets, right? Because, so we just inductively from n to the smaller numbers, you want to construct the tree labeling. So we can assume that for every this part and this part and this part, you have a tree labeling. But how to link them to make a one tree labeling? That's one thing. But the funny thing is that those guys have a property that they are separated by L plus 1 separation, but not separated by L separation, right? Or less, because the L restrictions are same. They do not have a separation of order L distinguishing them, right? So we can use the previous result for that. So what we do is that we denote the capital S by these red tangles, and then by the previous result, we can take a tree labeling for S, and then for each tangle in the T heading S, by induction, we can obtain a tree labeling for those cones. And then we can merge somehow like this. So this blue node, if you look at the blue node as a one node, this is the tree labeling for S. But for each guy, it has a tree labeling by induction. Yeah, for each of them. And then we link them in some way. Yeah. So this is the old thing, and then we have to change it to directed tree-decomposition. Probably I cannot explain. Yes. Yeah, there are some technicality there. So this is the statement, and then we have some nice application where we obtain an algorithmic version where we distinguishing only tangles of order 3k separated by some separation of order less than k, because to detect the tangles we use brambles, and there is this 3 blow up between the bramble number and tangle number. And we need some 3k here. And we obtain a half or no disjoint. We obtain a polynomial time algorithm for half or no disjoint passive problem, which asks for any pair of S1, T1, and S2, T2, and so on. You find the half integral linkage, or say there are no vertex disjoint passives. So we can solve this using the tangle tree decomposition, and then this is just a dynamic programming. And we also proved the half integral L-Bosa for directed OZ cycles. The reason why we use this tangle tree decomposition for L-Bosa is that this Kenichi and Stepan proved the directed grid theorem, but they didn't mention that there is directed grid theorem specific to some directed tangle, because tangle just defined now, right? So probably that can be proved. But at the moment we just use this decomposition theorem to prove this. Yeah, here is just some interesting problems. The first problem is that these undirected separations have a very nice property and actually generalized to the so-called abstract separation system by mostly worked by this test group. And it seems like we can prove all this theory for some abstract separation system with the x plus and x minus and so on. And I think we can do that, but we didn't do yet. Yeah, probably can you obtain something like this? And also one interesting question is that we don't know whether there is a polytime algorithm for half integral disjoint passive problem. So it says that either there are half integral linkage or say that there is no half integral linkage. And maybe some more Edo-Shposa or the half integral Edo-Shposa property, some variants of directed cycles. That might be interesting. And then we are actually trying to go further than this tangle theorem to obtain some structural theorem when we exclude some clique as a butterfly minor. And then also it may be combined with directed flat theorem, which we proved quite recently. Okay, thank you. Thank you very much.
Thank you very much. Questions?
Wow, that's clear. Plus 2 and type.
No, I don't think so. Yeah, just our proof gives that blow up. I don't know. We don't have a time to optimize. It's very technical to prove that part actually.
For the algorithm, you have. Can you go back one slide?
Sure. Yes.
Yes. So.
Yeah, so we guess all the parameters of order 3K or something like this, because the heating set has a size 3K. So we just guess, and we do not have to detect the parameters, but we just find the separation between those heating sets. And then
But that all, I mean, I was confused why you need the 3K, because if you can distinguish all tangles of order 3K, then you can distinguish all tangles of order K. So, or maybe I'm confused.
So we don't distinguish all tangles over 3K. All there are tangles of order 3K, but some pair maybe need 3K minus 2 or 3K. But we only care about tangles separated by order less than, separated by order less than.
You need a factor 3.
Yeah, so between the separation of order and then the size, the order of tangle, there are some 3 factors. Yeah, we do not have an algorithm that distinguishes all the tangles of order K.
Do you have an algorithm for deciding whether you have a tangle of order n plus K?
I think we can do that. I have to check. Yes, I think XP algorithm should exist.
Sorry. Yeah, maybe we can.
We can detect the parameter, but maybe not tangle. Yeah, I have to check.
Because you're canonical in the sense that when you have isomorphic graphs, then you get the same thing, or?
Yes.
Yeah, so that's actually we had lots of discussion. We call this canonical or not, and so on. But actually, the version for the Robertson and Seymour and version by the Discrete group, the meaning of canonical is slightly different because it's not preserved by automorphism for the Robertson and Seymour things, but the Discrete group extend this result by putting this canonicality. And here, I don't think so, because because even this m squared plus 2m, you put some arbitrary vertices and so on. So I think you don't have that property.
There's some duality theorem for the existence of directed tangles.
Yes. You mean either there are directed tree-decomposition? Yeah, there is a dual, because there was already proved by equivalence between directed tree with and Brember, and then we proved the equivalence between Brember and tangle.
Is it the exact theorem or is it rough duality?
A rough theorem. Yes. Yeah. Yes, I mean the tangle tree labeling will be like the dual object of tangle, probably.
All right, any other questions? So if not, let's thank the speaker.
Thank you.